This lecture will illustrate the concepts that are central to being able to test claims that are made by yourself or someone else, and being able to use a method to take sample data to test that claim to determine whether it is likely true or not. Hypothesis testing is the key component to inferential statistics, wherein you can test claims and determine whether there is enough evidence to reject a claim or not, or there's insufficient evidence to reject a claim, or there's enough evidence to support a claim, or not enough evidence to support a claim. A hypothesis is just the claim that is being made about the property of a population. Now, this could be a proportion, a mean, a variance. Some kind of claim is being made about some property of that population. And the whole point of this process is that we need to be able to test the claim that is being made in a systematic and objective way so that there is no inherent bias in our conclusions. And we need to determine whether the claim that is being made is consistent or inconsistent with available sample data. So the hypothesis test itself is the actual procedure, the step-by-step procedure. We're going to talk about 7 steps that you follow to build every single hypothesis test claim. And this does not matter if we're talking about the claim about a mean of a population or a proportion, or if it's a goodness of fit test to see whether a distribution that is a probability distribution that is claimed is actually fitting with the data, or whether it's a correlation test if you have a set of bivariate data and you want to know whether there is a linear relationship between the two variables, or a quadratic relationship, or an exponential relationship between the variables. A hypothesis test will let you use a specific set of steps where you take a random sample, calculate a test statistic from that sample, and determine whether the sample result that you get is likely to occur by chance, or whether it is a normal occurrence, meaning that it would be similar to what the claim is being made. If you end up with a highly unlikely result, then there are 3 possibilities or 3 possible explanations for this. It is always possible that a rare event actually did occur. So when you do your significance level, when you decide a significance level for a hypothesis test, this is talking about how likely are you to get a rejected null hypothesis by chance when the null hypothesis isn't actually false. And so when you are doing this analysis, the rare event, if you have a significance level of 1%, then there's a 1% chance that you are going to get a claim that does not agree with the sample 1% of the time. And so you could actually get a statistically rare event occurrence. It's also true, though, that if the probability of your sample statistic or sample result occurring is very, very low, it could mean that the hypothesis itself that you are testing is incorrect. It could be that that claim that's being made is wrong. There's also the possibility, though, that maybe your sample wasn't truly a random sample, or maybe the claim that was being made was based on assumptions that aren't actually true. So you always sometimes have to look deeper than just what the sample statistic tells you. You might have to check whether that sample was actually a random sample, or whether the claim that was being made was actually made from correct assumptions. So when we do a formal hypothesis test, we break the original claim into whether it has an equal sign or doesn't have an equal sign. If the original claim has an equality, mathematical equality expressed in it, it becomes what's known as the null hypothesis. The symbol for the null hypothesis is H sub 0 or H sub null, so null hypothesis. And this is the statement about the value of the population parameter that contains an equal sign. So this could be the statement about a proportion of a population or a mean of a population or a variance of a population, but it contains an equal sign. The alternative hypothesis is what is true if the null hypothesis is false. So it is the opposite of the null hypothesis. The symbol is H sub 1, and because it has to be the opposite of the null hypothesis, it can't have an equal sign in it. So it will contain symbols like greater than, less than, or equal to. So the original claim that is made can be either the null hypothesis or the alternative hypothesis. It just depends whether the claim that was made contains a condition of equality or not. So as an example, if we have a company that is producing an ergonomic computer mouse, and they claim that the mean lifetime of the mouse that they build is 24 months. In this claim, a claim is being made about the mean lifetime. So that's a claim about the population mean mu, and the word is indicative of a condition of equality. And so the claim that's being made is being made about the mean mu, and they're saying that it is 24 months. Because that claim contains an equality, it becomes the null hypothesis. The opposite of this claim would be what is true if this is false. The only possibility is that the alternative hypothesis is that the mean is not equal to 24 months. You could get a sample statistic that shows you having a lifetime much lower than 24 months or much higher than 24 months, either of which might lead you to the conclusion that the mean isn't actually 24 months. Another example would be, let's say you've got a company that's building flow meters for a fluid mechanics apparatus, and they claim that the average measurement uncertainty of this device is going to be less than 0.1 cubic meters per second. Again, this is a claim that is being made about average. So that's a mean claim, but the word here is less than 0.1 cubic meters per second. Because less than is not a condition of equality, in fact, it means that the claim about the mean of the population is less than 0.1 cubic meters per second contains no equal sign, then it must be the alternative hypothesis. The opposite of this, the claim that must be true if the alternative is false, would be the only other possibility is that the mean is greater than or equal to 0.1 cubic meters per second, and because that contains an equal sign, that would become the alternative, the null hypothesis. So in all hypothesis tests, you have an original claim that is made, and it will either be the null hypothesis if it contains an equal sign, or it will be the alternative hypothesis if it does not. When you do hypothesis testing, there are two types of errors that can be encountered. The first type of error is, let's say you happen to reject the null hypothesis, but it's actually true. So if that happens, if you reject the null hypothesis when it is true, that's called a type 1 error. It's also known as a false positive, and I'll explain that in a second. A type 2 error is when you don't reject the null hypothesis, but it's actually false. So you failed to reject the null hypothesis, but it's actually false. That's also known as a false negative. So this is a classic example to distinguish between a type 1 error and a type 2 error. Let's say a person walks into a doctor's office and they want to take a test to determine whether they are pregnant or not. And the idea is that you reject the null hypothesis based on sample data, based on some kind of test from the real world. And if, for example, a man came into this doctor's office and wanted to determine whether he was pregnant or not, and you reject the null hypothesis that he is not pregnant. So he comes in, the null hypothesis would be, well, he's not. The null hypothesis, the default hypothesis would be that the person coming into the office is not pregnant. If you reject that null hypothesis, you get a positive detection of pregnancy. But it's clear that if the man comes in, that he can't be pregnant. So that would be a type 1 error, a false positive. You rejected the null hypothesis that the person is not pregnant in favor of saying that they are, when in fact they are not. The correct outcome there would be that this person is not pregnant, so you could not reject the null hypothesis. And so you would not reject the null hypothesis, and so you would have no reason to reject the claim that they weren't pregnant. So that's this check mark. A type 2 error would be if a woman came into the office who was clearly pregnant, took a pregnancy test, and you found evidence to reject the claim that they were not pregnant. Okay, then that would mean that you reject the claim that they're not pregnant, then this woman is clearly pregnant. That is the correct outcome. The type 2 error would be if you failed to reject. You failed to reject the claim that they're not pregnant when they clearly are. So that's a type 2 error. It's a false negative. You get a negative result for pregnancy when in fact they actually are pregnant. A test statistic is obtained from the sample that you use to conduct your hypothesis test. So you have your claim, whether it is the null hypothesis or the alternative hypothesis. It turns out you only ever test the null hypothesis. So a sample statistic is used to determine whether you're going to reject the null hypothesis or not. And so the critical region would be the set of all of these possible values of the test statistic. It's usually a shaded region, a tail, a left tail or a right tail on your probability distribution, that if you find a sample that lies in that region, it will allow you to reject the null hypothesis because it is at such a low probability. The critical region is sometimes also called the rejection region for the null hypothesis. The significance level is the likelihood of rejecting the null hypothesis when it's actually true. That's a type 1 error. And usually you want this number to be very low, like 1%, 5%, 2%. These are very common significance levels. The significance level alpha is the likelihood of committing the false positive error. And so when you draw your probability distribution for your claim, this would be a claim. This is a two-tailed test that I've drawn here. So it might be the one where they've claimed that the mean lifetime is equal to 24 months. If you find a sample statistic that is very much larger than 24 months, then it might lie significantly away from the claim of the mean, which is in the middle, if it's too high, or if you get a value that is too low. Both of these regions are small probability regions related to alpha or alpha over 2 if there's two tails, that you are allowing a sample to disagree with the claim by chance. So the critical value is the actual value of the test statistic that's on that boundary. It separates the rejection region from the non-rejection region, the critical region from the acceptable region for the null hypothesis. So it will be the value of the test statistic that lies specifically at those boundary points on your critical region. So here is the hypothesis testing procedure. You will use this hypothesis testing procedure for every hypothesis test, whether you're making a claim about a mean of a population, the proportion of a population, a variance of a population, whether you're making a claim about whether two variables are correlated, a set of bivariate data, are they related to each other linearly? Are they related to each other by a quadratic? Are they related to each other by an exponential function? Or whether you're trying to fit a probability distribution to a observed relative frequency in each category. That's a goodness of fit test. It's also an hypothesis test. So here's the 7-step procedure that we will follow for every single hypothesis test. And the first step, is to identify the claim. So that is simply reading the statement that is being made and identifying what claim is actually being made and whether it contains an equal sign or not. So you identify the claim that's being made, you write it down with mathematical symbols. If it's a claim about mean, you'd use symbol mu. If it's a claim about population standard deviation, you would use sigma. If it's a claim about population proportion, you would use p. So you identify the claim that's being made, you write it down with mathematical symbols. Then, based on whether that claim has the equal sign or not, you need to identify both the null hypothesis and alternative hypothesis. Remember, you distinguish between the two. Which one contains the equal sign is always the null, and the one that does not contain the equal sign is always the alternative. Then you need to either select or identify. Many questions this will be given to you, but if you're doing this in real life, you would have to select the significance level. The significance level alpha is the probability of committing a type 1 error, getting a false positive, where you'll reject the null hypothesis, you'll reject the claim of the null hypothesis based on the sample data, but based on random chance. So you want that probability to be relatively low so that it doesn't happen too often. Then you identify which test statistic is actually used in this test. So when we do tests of claims about means proportions, we usually use a z-test or a t-test, depending on whether what the sample size is and whether the standard deviation of the population is known or not. If we're doing a goodness of fit test, it would be a chi-squared test. If we're doing the correlation coefficient test, we might use the critical values for the correlation coefficient. So you have to determine, is this a z-test, is this a t-test, is this a chi-squared test? And later on in the course, we will go through all of the different variations of the tests so that you know which one to actually use. Step 5. You want to find the critical value of that test statistic. So that's the value that's on the boundary between the critical region and the non-critical region, between the rejectable region. If you find a sample that lies in that region, it would disagree with the null hypothesis. versus if you find a sample that lies in a region that agrees with the null hypothesis. You draw the graph showing your distribution, show your test statistic, show your critical value and the shaded critical region, and usually you will look up on a table of some kind to determine what that critical value of the test statistic is. You would look up on the Z table for specific probabilities that are in the tails to find what the critical Z value is in an identical fashion to the way we did it for estimating population means using confidence intervals. Okay, then you make a decision. If your sample lies in the critical region, you will reject the null hypothesis. If your sample does not lie in the critical region, you won't reject your null hypothesis. The point is, you only reject or not reject the null hypothesis. You do not make a decision based on the alternative at any time. The sample statistic that you get is always made in relation to the null hypothesis. So if the test statistic lies in the critical region, you're going to reject the null hypothesis. If it doesn't lie in the critical region, meaning it's between the two limits, that is in accordance with or not significantly different from the null hypothesis, you cannot reject the null hypothesis. And so those are the only two possibilities. You either reject the null hypothesis or you don't reject the null hypothesis based on where the sample lies in your distribution. Okay, now you have to write a conclusion. Writing the conclusion is where you basically take the claim that was made originally and write a conclusion about that claim based on the results of this test. But remember, you can only reject the null hypothesis. So if your original claim is the null hypothesis, you're only ever going to reject or fail to reject that claim. But if your claim is the alternative hypothesis, which must be true if the null is false, then you will be able to determine whether you have evidence to support the alternative hypothesis original claim or fail to support the original hypothesis, the original claim that is the alternative hypothesis. To summarize that, because that sounds kind of confusing, here's the wording of the final conclusion is based on this final table. Remember that you only ever test the null hypothesis. So when you're asked the question, do I reject the null hypothesis? The answer is either yes or no. But based on whether your original claim is that null hypothesis, you'll get a different conclusion. If your original claim is the null hypothesis and you rejected that claim, then you would have a conclusion there is sufficient evidence to reject that null hypothesis. If your original claim is the null hypothesis and you did not find enough evidence to reject that claim, then there is not sufficient evidence to reject the claim of the original null hypothesis. If your original claim is the alternative hypothesis and you end up rejecting the null, that means that the alternative must be true. So if you reject the null hypothesis, then you will have sufficient evidence to support the original claim, which is the alternative hypothesis. If your original claim is the alternative hypothesis, but you don't reject the null, that means the opposite can't be, there's not enough evidence to show that it's true, so there is not sufficient evidence to support the claim that the alternative hypothesis is true. So there are 4 possible conclusions based on whether you reject or don't reject the null hypothesis and whether your original claim is the null or alternative hypothesis.